Welcome back, everyone. This is my attempt at a summary of Chapter 3, where we started talking about algorithms, and more or less the tools for how we talk about algorithms. So we began by talking about how there's a lot of different dimensions in which you could talk about what makes an algorithm good versus bad. And we've chosen here to mostly focus on one very narrow part of an algorithm, which is the amount of time it takes for the algorithm to run. And so we're going to be interested in sort of the running time, or we decided to sort of measure the number of steps. Now, the reason for taking number of steps instead of running time is that the number of steps should theoretically not really depend on what kind of computer you're talking about, versus running time will depend on the processor and all of that kind of thing. And in particular, what we're interested in is how this number of steps scales with the size of the input. Just as an example, and this is our favorite example because we talk a lot about trial division, which is this algorithm where to either decide if a number is prime or to factor it, it works equally well for both. You just keep dividing the number by 2, then 3, then 4, then 5, until you get up to the square root of the number. And then you write down all the factors, and so you can factor it, or you can see if there's any factors to see if the number is prime. And so in total, this takes square root of n divisions to factor n, or tell you if it's prime. Already there's a little bit of ambiguity in this because of this number of steps being what we're counting. Here we're talking about divisions, but you might slice this up slightly differently, and if you did, you might get a slightly different answer for how many steps this thing is. Ultimately, when we're talking about comparing the running times of algorithms, we're going to be talking about it in very, very rough terms, so this kind of difference we're hoping is not going to matter too much. But be warned, you might see different answers depending on exactly how someone chooses to slice up one of these questions. Now, next I want to note the distinction between the input and the size of the input. So this n here, this is the input. But when we talk about size of input, because we want this to apply to all algorithms, we're actually going to be talking about the number of bits in the input. So I have usually tried to stick to capital N for that, to remind you that capital N is a number of bits, not a number. I mean, the number of bits is a number, but it's not the number we're actually putting in. And this is on the order of the log base 2 of n. Roughly speaking, if you want the number of digits in a number, you take the log base 10 of it. If you want the number of bits in a number, you take the log base 2 of it. Of course, this number is not an integer, so it's going to be a little bit off, plus or minus 1. You can figure out exactly what it is in terms of ceilings and floors if you want, but we're going to be doing lots of rounding here anyway, so I'm going to just deal with log base 2 of n. Now, one thing we note very quickly is that counting the number of steps involved in running an algorithm gets very cumbersome very quickly. And so we end up sort of simplifying this by using this weird thing that we call big O notation. And so the way we write something in big O notation is to write something like this, where the variable might be x or n or whatever. And we write it in this strange way where we use this equal symbol, even though I would encourage you to not think of this as ever really meaning anything is equal to anything. But rather, this is describing a property of the function f that the function f has relative to the function g. So, in fact, I think it's maybe best to think of O of g of x as the set of functions with this property, and really what you're saying is that f is one of those, so f is an element of that set. But whatever combination works for you. But what does it mean? What it means is that there exists some constant, which we just call m, with the property, the size of f of x, where I'm just putting absolute value bars here around it just to denote the size of it, rather than having a sign floating around, is less than or equal to that constant times the size of g of x. And this is true for all big X. Again, this notation does not at all see what happens for small inputs, it only sees what happens for large inputs. So it maybe makes it a little easier if you just realize you can just ignore every x less than 1,000,000 when you're talking about this notation. So the way you mentally should think of what this is saying is that f of x is not that much bigger than g of x. Or f of x is no more than a constant times g of x. Or if you want to think what this O is really standing for is the word order, and so if you're talking about the order of growth, what this is really saying is the order of growth of f of x is less than or equal to the order of growth of g of x. Now, when we say a function is O of n, for example, what we're saying is that that function grows at most linearly in n. So if, for example, I draw you here, this is y equals n, this is y equals 2n, which is just a constant times n that I picked. If I draw in some weird-looking function that does something like that, this function is O of n, right? This function is often bigger than n, but it's always smaller, at least in the window that we can see, than 2 times n. And so what's really useful about this notation is I don't need to understand the exact number of steps that go into an algorithm when I want to talk about the running time. I only need to be able to give it very, very roughly. And so that lets me sort of bulk together a bunch of different functions and talk about them sort of all together at once. And so anything that's O of n, we're going to call that linear running time. Likewise, anything that's O of a power of n, we're going to call polynomial. Again, note, that doesn't mean the function is a polynomial. It just means the function grows at most as quickly as a polynomial would grow. Something that's O of e to the n, we call that exponential. Something that's between polynomial and exponential, we call sub-exponential. And something that grows faster than an exponential, we call super-exponential. Now, so far, algorithms we've talked about have largely been one of two things. They have been either O of n or O of e to the n. And I want to emphasize that these two things are really a world different in terms of what they're saying about the algorithm. Things that are O of e to the n include trial division. And this is an important point because you might be thinking, oh, you wrote down just a minute ago that trial division takes square root of n steps. So that should mean trial division should be O of square root of n. And O of square root of n should certainly be O of n. And so I was thinking trial division was going to be over here. But note, this is where the little n versus big N distinction comes in. So when I talk about trial division and how many steps it takes, it's taking square root of the number steps. Whereas when I'm talking about algorithmic efficiency, usually the convention is that we're going to describe that in terms of the number of bits in the number. And so if we remember that big N is approximately the log base 2 of little n, and we want to think about the relationship the other way, then what we get is that n is approximately 2 to the big N. And so that's why when I wrote this down, I wrote O of e to the n. And notice 2 to the n and e to the n are slightly different, but we're just going to batch all the exponential functions together into this class when we talk about things that grow exponentially. Now, roughly speaking, the difference between these two is again describing how they scale with the size of the input, but something that's O of n, we should expect to be able to do in a reasonable amount of time, even for very, very large inputs. So one of the things we talked about, being O of n, is the Euclidean algorithm. And in the video, I show you that the Euclidean algorithm works just fine for numbers that are 5+ million digits long. You can do it in under a second in Sage, no problem. On the other hand, trial division stops working in under a minute even for something like a 20-digit number. So that's a world of difference between something that's already choking out at 20-digit numbers versus something that's chugging along quite happily at 5 million digit numbers. I think the way to make this clearest is to think what would happen to each of these algorithms if you doubled the input. Let's just forget about the O for a second. If my algorithm takes an amount of time n, and I double n, then I would double the amount of time in the algorithm. So that's to say if you went from a 5 million digit number to a 10 million digit number, you would expect the running time to double. So if it took a second to do 5 million digits, you might expect it to take 2 seconds to do 10 million digits. On the other hand, if you have an algorithm that, and again, we're just going to forget about the O for a second, has a running time that grows exponentially, if I double n, then e to the n becomes e to the 2n, which is actually e to the n squared. And so what this is saying is that, in fact, doubling the size of the input will square the running time of the algorithm. And you can see why that is much, much, much worse. Every time you double the size of the input for an algorithm that's O of e to the n, you increase the running time by an astronomical amount. By and large, we're going to view algorithms we talk about as living somewhere on a spectrum between at the very fast end being O of n, and at the very slow end being O of e to the n. And so you might imagine that there's this sort of number line where sort of on one side of the number line is O of n, and on one side of the number line is e to the n, and anything we put over towards this side of the number line, we're super happy with. And then the more we creep up towards the e to the n side, the faster we become unable to handle the question at all. Now, I did want to briefly address the limitations of this notation. And there are a lot of limitations of this notation. So one limitation I already mentioned is that big O notation just does not see what happens for small inputs at all. So it is possible to vastly improve the performance of an algorithm for inputs, say, less than a terabyte in size, without affecting the big O notation at all. However, for all practical purposes, basically all inputs are less than a terabyte in size, and so doing so might vastly improve the practical ramifications of using the particular algorithm. This also applies to things which fit the real world better. So we talked about sorting algorithms a bit, and we talked about how a lot of the best improvements in sorting algorithms aren't really affecting the big O notation of the sorting algorithms at all. They're just fitting the real world data that actually happens when people use sorting algorithms better. To make this particularly alarming, I might even add that, let's say, as a programmer, you manage to take an algorithm and you make the algorithm 10 times faster. Any programmer would be ecstatic if they were able to make their big computation run 10 times as quickly. But running 10 times as quickly is completely invisible to the big O notation, because remember, this big O notation includes multiplication by any constant. And so speeding something up by a factor of 10, though practically very relevant, does not show up in this notation at all. Also, in the process of focusing on running time, we have neglected the fact that algorithms have lots of other qualities that we might like to optimize. So one of those is memory. I might be able to make an algorithm go from taking up a large amount of memory to taking up a small amount of memory, and that might not affect the running time at all, or it might even make the running time a bit worse, but still, the trade-off might make it far better for all practical purposes. So, in short, for talking about how algorithms scale, the big O notation is very useful. For talking about practical use of algorithms on a particular size of input, big O notation is useless. So if, for example, I said, okay, I'm going to get 4096-bit numbers all day, and I want to factor them as quickly as possible, I would not go and look at the big O notation for how long it's going to take in the longest run to decide which algorithm would be best for factoring my 4096-bit numbers. Because 4096 is a specific size of input, and so, likewise, if I looked at factoring 100-bit numbers, there might be a very different algorithm that's best for that problem. So, for a particular scale of problem, you need to look at something other than the big O notation. But when we talk about things completely agnostic of scale, this tells us what's going on in a very useful way. We've been alluding since the beginning of the course to the fact that certain calculations are easy and certain ones are hard, which roughly you can think of, again, as where they fall on this line between being linear, which would be great, and being exponential, which would be terrible, and somewhere in between, potentially. And so, some of the easy operations include multiplication, GCD, modular inverses. Of course, modular inverses are easy because the extended GCD is easy, and the extended GCD is all you need to do to calculate your modular inverses. Modular powers. That's owing to the repeated squaring algorithm, which I'll review for you in a moment. And primality testing. On the hard side, there are two problems we've come across a lot, which are factoring and the discrete log problem. Now, there's a lot to look at here, but one thing I want to note is both of the things that are in the hard category are undoing something that is in the easy category. So factoring is just undoing multiplication. If I take two huge numbers and I multiply them together and then give you the product and say factor it, I'm asking you to undo the thing that I just did. And the fact that multiplication is here in this easy column tells me it was easy for me to multiply them together, and it will be hard for you to factor them. The discrete log problem is asking you to undo modular powers. So if I take some primitive root mod prime and I raise this to some gigantic power, that's going to be easy for me. But if I then show you the result of my calculation, where I calculated 2 to this giant power, and say, okay, now what was the power? Then suddenly that question is very, very difficult. At first, it might seem completely paradoxical that it can be easy to go one way and hard to go the other direction. It might seem almost impossible to imagine that at first, but it's in fact the basis of all cryptography, is that there are calculations which are easy one way and hard the other way. And in a way, you can think of this as being like smashing a glass against the floor. It's very easy to smash a glass against the floor. It's very hard to put the glass back together. I now want to review why it is that primality testing and modular powers are easy for us. So let's start with modular powers and this whole idea of repeated squaring. So let's say I want to calculate 7 to the 120th power mod 201. Now, nominally, the way I would do that would be to calculate 7 to the 120th power, and then mod the answer by 201. And I should have mentioned, by the way, I did not. Modding is also easy. So mod something by something else. That is an easy calculation. The reason why I don't want to do that is because that would require doing 119 multiplications. And I don't want to do 119 multiplications in order to raise a number to this power, because that's going to scale very poorly with the size of this power. And preview, or reminder, the reason why we're talking about this is because our primality testing algorithm requires raising a number to a huge power to decide if a huge number is prime or not. So I cannot rely on something that's going to scale linearly with my number. So how are we going to calculate this in a much, much smaller number of multiplications? Well, the first step is that we're going to write 120 in binary. So you might not have thought before about how do I write a number in binary, but it's actually not so bad. You want to just figure out what is the largest power of 2 that is less than or equal to 120. And in this case, that largest power of 2 is 64, because the next power of 2 would be 128. So I'm going to write 120 is 64 plus, and now I've got to figure out how to write the rest of this. So 120 minus 64, that is, it looks like 56. So now I want to do the same thing. What's the largest power of 2 that's less than 56? And the answer will be 32. So now what's left? 56 minus 32, which happens to be 24. So what's the largest power of 2 that's less than 24? Well, as it would happen, it is 16. 24 take away 16 is 8. What's the largest power of 2 less than or equal to 8? It is 8. And now I'm done. I've written 120 as a sum of powers of 2. So this is 2 cubed plus 2 to the 4th plus 2 to the 5th plus 2 to the 6th. So when I go to write this in binary, I'll ask, okay, how many 0th powers of 2 did I use? That's how many 1s did I use? I used no 1s, so this is a 0. How many 2 to the 1sts did I use? I used no 2 to the 1sts. How many 2 squareds did I use? I used none. Okay, how about 2 cubeds? I used one of those. 2 to the 4ths, I used one of those. 2 to the 5ths, I used one of those. And 2 to the 6ths, I used one of those. So this is 120 written in binary. Now, I'll remind you, this is a step for humans, not a step for computers, because the computer is already storing this number in binary. The computer doesn't think in base 10. So remember, what I want now is to calculate 7 to this power mod 201. And to do this, what I'm going to do is repeatedly square 7 mod 201. So the first thing I get is 7. Then I will get 49. I'm now going to square 49 mod 201, and that will give me 190. Notice 49 squared itself is a quite large number. It is 2401. But I get the benefit that I'm working mod 201, so I don't have to keep track of the huge part. I only have to keep track of the mod 201 part. So that's why I have this 190 here. Next, I calculate 190 squared mod 201. And when I do that, I get 121. So then I calculate 121 squared mod 201. I get 169. And then I calculate 169 squared mod 201. And I get 19. And finally, I calculate 19 squared mod 201, and that gives me 160. How do I know this was my right place to stop? I know that's my right place to stop because the highest power of 2 that I used in my binary expansion was 2 to the 6th. So I need a total of 6 squarings of 7. Now, just to keep track, so far, we have done how many multiplications? And, well, the answer is 6. Each squaring is one multiplication. 7 times 7, 49 times 49, 190 times 190, da-da-da. So far, we've done 6 multiplications. How are these numbers I've calculated going to help me? And the key to unwinding that is writing down what these things actually are. So this is 7 to the 1st. That's 7 squared. This is 7 squared squared. So this is 7 to the 2 squared. Also known as 7 to the 4th, but I want this power to be clear. So this is 7 to the 2 to the 0th, 7 to the 2 to the 1st, 7 to the 2 squared. If I square 7 to the 2 squared, you can check that I get 7 to the 2 cubed, 7 to the 2 to the 4th, 7 to the 2 to the 5th, and 7 to the 2 to the 6th. So that's just labeling what all of these numbers I have written down are. And now the key thing is that I know how to use those numbers to make 120, so I'm going to know how to use those numbers to make 7 to the 120th. Namely, I'm going to do that as follows. 7 to the 120th is the same as 7 to the 64 plus 32 plus 16 plus 8. And by my properties of exponents, that's 7 to the 64th times 7 to the 32nd times 7 to the 16th times 7 to the 8th. Now, what's that? Well, 7 to the 64th, that's 7 to the 2 to the 6th, that's 160. Times 7 to the 32nd, that's 7 to the 2 to the 5th, that's 19. 7 to the 16th, 7 to the 2 to the 4th, that's 169. And 7 to the 8th, 7 to the 2 cubed, it's 121. And then you can calculate, that is 82. And I want to remind you, every single calculation here is happening mod 201. And that's really important because 7 to the 64th power is a pretty large number. It is more than 30 digits. I don't want to think about what 7 to the 64th power actually is. I certainly don't want to write down the digits of it. But because I know everything here is happening mod 201, I get to, at every step here, mod my answer by 201. So I did this mod 201, mod 201, mod 201, mod 201, mod 201, mod 201. And likewise, when I'm multiplying these, I get to do each step of the multiplication mod 201. And how many multiplications is that? Well, it is 3 more multiplications. So in total, how many multiplications did we do? 9. So when I originally wrote down 7 to the 120th mod 201, if we'd done this directly, we would have done 119 multiplications. But because we were clever and used this repeated squaring idea, we did the same calculation. We got the same answer we would have gotten if we'd done those 119 multiplications, but we did it in 9 multiplications. And so this is the repeated squaring algorithm. And you can see how this works in general. You write the number in binary. That tells you how many times to square it to write down the powers that you're going to need. And then you multiply together just the powers that you need out of that in order to make your original power. And so what's the moral of the story here? If you want to raise a number to a power mod another number, the work that goes into that grows as, well, the number of multiplications was, in fact, always less than or equal to twice the number of bits in the number. And twice the number of bits in the number, that's just going to be twice the log of the number. But remember, the big O notation eats the 2 times. And so modular exponentiation, that is, raising some number a to the kth power mod n, in fact takes O of log of the power work. Now, this last fact here is important because it plays into the reason why we're able to do the calculations that we need in order to make our first primality test work. Or I should say, our first reasonable primality test. And so how does the Fermat test work again? We take in some number n. We want to decide if n is prime. We choose some a between 1 and n, randomly, or the smallest one we haven't chosen yet, or whatever. And then we calculate this a to the n minus first power mod n. Now, because of what we just said, we know that this step of raising a to the n minus first power, which is going to be the bulk of our work in this algorithm, that is O of log of n, but that just happens to be saying that this is O of n, the number of bits in the number we want to decide if it's prime or not. Remember our capital N from before. So doing this power operation as part of the Fermat test is O of the number of bits of the number we're testing for primality, not O of the number we're testing for primality. So, Fermat's little theorem tells us that if n is prime, then a to the n minus 1 will always be exactly 1 mod n. And so if I happen to calculate this a to the n minus 1, and it isn't 1 mod n, that tells me n can't have been prime. And so at that point, if I see that, I stop my program immediately, and I say, okay, n is definitely composite. I'm happy. We can go home. If, on the other hand, a to the n minus 1 is 1, well, that doesn't quite tell me anything. So what I might want to do is I might want to go back and choose a different a and try again. And so what I'll write is repeat until satisfied. And once you're satisfied, you're not allowed to say n is definitely prime. What you are allowed to say is n is probably prime. And this probably isn't like a coin flip. This probably is some very vanishingly small percentage chance that you somehow got tricked. The chance exists, but you're very unlikely to fall into it in practice. Now, however many times it takes for you to feel satisfied, if you're going to run this 10 times or 20 times or 80 times or whatever, that number is still going to only multiply this O of n by a constant. And so that means that this test for primality is in fact itself O of n. And so in fact, what we've really just done here is to justify the fact that I put primality testing in the easy column. Because, remember, my easy column here was supposed to correspond to things that were closer to the n side than the e to the n side on the O of n versus O of e to the n. And I just showed you that primality testing can be done in something like O of n. Now, there is a little tiny asterisk there, and the little tiny asterisk there is, well, this works most of the time, but sometimes you get unlucky, and you may get really unlucky. And so some very, very, very small percentage of the time, you're going to say, this number is probably prime, and it's going to turn out the number isn't prime at all. So this is a very good primality test, but it's not a perfect primality test. Being that you're in this class, likely you're a mathematician at heart in some sense. And so mathematicians have this really strong boundary between things that are true and things that are false. And in 220, for example, you probably talked about how if you're looking for a for every statement, even one counterexample makes it false. All it takes is one counterexample for Goldbach's conjecture to be false, or the Collatz conjecture, or any of these other famous conjectures. They're instantly completely disproven by one counterexample. And so, in your heart of hearts, if you think about this, from that perspective, you might say, okay, the fact that this algorithm is sometimes wrong completely invalidates its use. However, from a practical point of view, an algorithm that works 99.999999999% of the time is great. And we're perfectly happy with it, and we're perfectly happy with how fast this algorithm is able to do that. Now, there's two different ways you could look at the problem of, okay, so sometimes it's wrong. Imagine I encountered some random number, and it passed this test, say, 10 times. Well, then your number is almost certainly prime. Again, 99.99999% chance your number is prime, as long as your number is relatively large. But there's another way to look at this, which sounds like it's asking the same question, but isn't. Which is, if I have a particular composite number, what is the probability that this algorithm identifies that it is composite? And now, for most composite numbers, the probability is very high. Again, 99.999, whatever you want. But it is true that there are some numbers for which this test will almost always say that they are prime, even though they're actually composite. And these numbers are called Carmichael numbers. So Carmichael numbers are composite numbers with the weird property that this primality test is going to falsely report them as prime the vast, vast majority of the time. In fact, another way to say it, the only way that you detect that a Carmichael number is composite with the Fermat test is if you are so ridiculously lucky that the A you choose shares a common factor with n. And that's just very, very, very unlikely to happen. Because if you have a large number and you want to know if it's prime, you probably already know it doesn't have any small prime factors. So probably your number is either prime or it's a product of 2 or 3 really big primes. But if the primes are really big, the probability that A, that I've chosen, is divisible by them is really, really small. In fact, probably, the A's I'm choosing, I'm probably starting at 1, trying 2, then 3, then 5, then 7, and so on down the line. So probably, actually, the probability might literally be 0 if I'm starting with the small A's. So that's really unfortunate, because it means in a certain sense that you might get not just unlucky, you might get really, really, really unlucky with your Fermat test. And in fact, there are infinitely many Carmichael numbers. So there are infinitely many of these numbers laying out there that will just sort of spring a trap and catch you unprepared if the only thing you come in with is the Fermat test. So again, that might seem alarming, but from a practical point of view, Carmichael numbers are incredibly, incredibly rare. And the chance that you come across a Carmichael number in the wild is significantly less than the chance that you get hit by lightning twice. So, on the one hand, these numbers are out there, but on the other hand, practically, unless you go out specifically looking for them, you're not going to find them. Still, this asterisk and the fact that Carmichael numbers exist gives us a sense that we might actually want a slightly better primality test. And we will later, after we talk about quadratic reciprocity, talk about a better primality test that can detect Carmichael numbers. And so we'll actually find a test that will always catch composite numbers at least 99.99999% of the time, even any particular composite number, so that we won't have to worry about this anymore. Repeated squaring is the simple algorithm that keeps on giving, because not only does it let us find gigantic primes, which are necessary for the algorithms that are based on the difficulty of factoring, it also lets us find primitive roots, which are necessary for the algorithms that are based on the discrete log problem. And so actually, whichever one of these easy-hard pairs you want to look at, we need repeated squaring in order to make the easy half of the easy-hard pair easy. So reminder, we want to go ahead and start with a large prime p, and then our goal is to return a primitive root. That is, a number where g to the x has period p minus 1 mod p. So the first thing we have to do in order to find a primitive root is we have to just guess one. Now, there's no reason you have to be smart about this guess. Primitive roots, not only are they guaranteed to exist, they're also guaranteed to be fairly common. So we're just going to guess a random number mod p. You might, for example, guess 2, then 3, then 5, and so on. But if you prefer to do it randomly, that's fine too. We're just going to guess one. And I suppose technically I should have said this as step 1. We're going to factor p minus 1. More on that in a moment. But I'm going to write the prime factorization of p minus 1 as a product of primes, which I'm going to call q1 to the e1 up to ql to the el. So then I'm going to take my x, that was my guess, and I'm going to raise it to this number, which is almost p minus 1, except that I've taken away q1. In fact, if you want, I could write this same number as x to the p minus 1 divided by q1 mod p, but you have to agree with me that this number is an integer in the power. And the reason for that is if this number is not an integer, then this doesn't mean anything. So I need to calculate that. And I'm also going to calculate that, which is an integer for the same reason. And that. All of these mod p. So if any of these are 1, then x is not a primitive root. And as soon as you see your x is not a primitive root, so really, as soon as you calculate one of these and it's equal to 1, you go back to step 1, and you guess a different primitive root. But if none of these are 1, then x is a primitive root. And so then we can go ahead and return x as our answer for our function. Now, you might briefly ask, why does that work? And so the key thing to remember is, I'm looking for a number whose period is p minus 1. And the period is how long it takes this function g to the x to repeat. Or remember that right before it starts repeating, it hits 1. So it's really asking when the first time g to the x hits 1 is. But remember what Fermat's little theorem tells us is that this period always divides p minus 1. So it might not be p minus 1, but it always divides p minus 1. So to show that g is primitive, all I have to show is, in fact, that g to every divisor of p minus 1 is not 1. Now, what you notice eventually, that saves you a little bit of more work than just checking all the divisors, is that, in fact, if you check the maximal divisors, that is, the divisors of p minus 1 that are missing only one prime factor, that's enough. Because if g to any divisor of p minus 1 is equal to 1, g to one of these divisors will be equal to 1. And then we will identify that it is not primitive. And so, unlike our last algorithm, there's no chance of failure in this algorithm. We are 100% guaranteed that we're going to find a primitive root, and once the algorithm says it's a primitive root, we're 100% guaranteed that it really is a primitive root. But, as always, there's an asterisk. The asterisk is that factoring p minus 1 is hard. See our earlier table, where we talked about easy things and hard things, and p is supposed to be a large prime, so factoring p minus 1 should definitely be hard. And so that breaks this entire algorithm, in the sense that if I start with a random large prime, I'm never going to be able to factor p minus 1, and then I'm not going to make it out of step 2 of this algorithm. There is a bright side, however. And the bright side is that, although factoring large numbers is in general difficult, there are many large numbers that we could factor very easily. So, for example, 1,000,000 factorial is a 5.5 million digit number, and yet you know exactly how it factors. It's already written as a product for you, and so you just have to factor each number that's less than 1,000,000, and well, that's not so difficult. And so even though this number is preposterously enormous, it would be very easy for a computer to factor it. So when we go looking for a primitive root of a large prime, what we actually have to do is realize that we can't just input a random large prime here. If we input a random large prime, then p minus 1 is going to be large, and then we're not going to be able to factor it, and then we're going to have a bad time. But if instead of that, we deliberately look for primes where p minus 1 is easy to factor, then we can find one of those primes, and then run this algorithm on that, and then everything is easy, because all we have to do is raise things to large powers, and that's repeated squaring, and that we can handle. So what do I mean by primes of special form? Well, you might, for example, go digging for primes of the form 2 to the k plus 1. Note, we quite often talk about Mersenne primes, which are actually the primes of the form 2 to the k minus 1. That's not super helpful here. But if you look for a prime of the form 2 to the k plus 1, well, if I find one, I 100% know how to factor p minus 1, because p to the minus 1 is in fact 2 to the k. This, as it happens, is not super useful, because all of humanity in total knows 5 primes of this form, and the largest one is not very big. But we can modify this recipe just a tiny bit, and instead write p is some constant, say L times 2 to the k plus 1, where this L is, say, less than or equal to 100. And it turns out that in practice, there are lots of primes of this form, and it is just as easy to factor p minus 1 for one of these primes, because here, of course, p minus 1 will work out to be L times 2 to the k. All I have to do here is factor L, and lo and behold, L is a 2-digit number, so you can factor it even by hand. So this is one of the ways you can go about finding a prime that will be well suited for the primitive root algorithm, is to go fishing for primes of specific forms where as soon as you find one, you already know the factorization of p minus 1. Another way that you might get lucky is that, remember, we know how to test for primality. So in other words, we know how to factor primes, which sounds weird at first, but if you're a factorization algorithm and I hand you a giant prime, your job is easy, because the first thing you do is check that the number I've given you is prime, and then you just say, okay, it's factored, and then you hand it back to me. And so as a result, another way we might simplify our lives is to find a case where p minus 1 is prime. Again, let me just walk you through that. If p minus 1 is prime, then I can just figure out that p minus 1 is prime. And then I know how to factor p minus 1 because it just factors p minus 1. Now, unfortunately, there's only one prime where p minus 1 is prime. And that's because, of course, most primes are odd, so p minus 1 is usually even. And so that doesn't work out so well. But if instead we look for p minus 1 is twice a prime, we can find lots of these, and these in fact go by the name Sophie-Germain primes. So basically what this is saying is, okay, so p is some large odd number, so of course p minus 1 is divisible by 2, so divide it by 2, and then check if that number is prime. And if that number is prime, and p is also prime, then you know how to factor p minus 1, namely p minus 1 factors as 2 times q. And so either primes of this form, or Sophie-Germain primes, are very useful for, again, finding a large prime where you can find a primitive root so that you can use the discrete log problem, and all of these good things follow from doing that. One great thing I should note about these discrete log-based algorithms where you need a giant prime where you know the factorization of p minus 1, so basically you need a giant prime with a primitive root, is that two different people can use the same prime and the same primitive root. So you don't in fact even have to find the prime, someone else can find the prime for you and then you can use it. In fact, something that's not too uncommon, or at least used to not be too uncommon, I think they do this less nowadays, is that they would build computer chips specifically with doing these kinds of calculations, mod a specific large prime, just so that they could do it as quickly as possible so that they could handle these kinds of algorithms. As a last note, I want to talk about actually using this stuff to do cryptographic things. So our first example of a cryptographic thing we're going to do is going to be based on the discrete log problem. Every cryptosystem you ever look at, you should immediately ask yourself, what hard problem is this based on? And so Diffie-Hellman is based on discrete logs. And the goal of Diffie-Hellman is actually not to send people messages. The goal of Diffie-Hellman is to agree on a shared secret. So in other words, it might be the case that you and your friend want to agree on a password that only the two of you know. And so you might do this someday on the phone with someone else listening or whatever, and you might come to an agreement on a particular 10-digit number that is your password. And then, when one of you sees the other or is texting or whatever, you could give the password, and you would know the only person who could possibly have that password is your friend. And that seems a little bit weird, but I'm going to show you how to do it. Another thing you could do is you could use that agreed password as the key to a different cryptosystem. So you could use that as a way of encrypting and decrypting stuff. So very early in the class, in fact on the first day, we talked about a one-time pad. And what a one-time pad was a way of taking some string of zeros and ones, which is my sort of key, and then you take the message, and then you just add these things together mod 2. So there's the key, there's the message, here's the encrypted stuff. And so here's the idea. You and I both know this. I want to send you this. So the way I send it to you is that I actually send you this. But remember, you also know this. So what do? You take the same key that I use to encrypt it, and you add these things mod 2. And when you do that, you recover the message. And so in this way, as long as both you and I know this key, I can send you this message, and as long as no one else knows the key, it's perfectly safe. And the reason why this works, by the way, is because what have I done? I'm this whole time adding mod 2, and so if I add this thing to it, and then you add that to it, then what have we done? We've added this thing twice mod 2, but 1 plus 1 is 0 mod 2, and 0 plus 0 is 0 mod 2. So basically, by adding it again, we undo the operation. So any of the symmetric key cryptosystems, so to speak, are going to be based on this idea of both of us having this secret combination of bits that no one else has, although in all likelihood you're going to do something more sophisticated with it than this. But that was all a long aside about what we're going to do once you and I have a shared secret. But how do we get the shared secret? Well, the way we get the shared secret is by using this algorithm, Diffie-Hellman. And so to start with, the two of us are going to agree on a large prime P and a primitive element G. So both of us have to be in agreement. This is the primitive element, this is the prime. Each of us is going to choose a random number less than the prime. So I'm going to call the numbers we choose A and B. Again, following the convention that usually when two people are talking to each other via a cryptosystem, we usually call them Alice and Bob, so I'm just going to honor that in A and B. Note A and B are huge numbers, because they're random numbers less than P. You don't have to interpret random super literally here. But they should be unguessable numbers, so they should be really large, giant numbers. So Alice sends G to this giant power mod P to Bob, which, note, Alice needs repeated squaring to do this, because otherwise she couldn't calculate this. And Bob, at the same time, sends G to the B to Alice, again using repeated squaring. So now what does Alice know? Alice knows A, because she came up with A, and Alice knows G to the B, because Bob sent it to her. And so, with that information, Alice calculates G to the B to the A. What does Bob know? Bob knows B and G to the A. He knows B because he came up with B, and he knows G to the A because Alice sent it to him. So Bob calculates G to the A to the B. And now the key observation here is that G to the A to the B is G to the A times B, which is the same thing as G to the B to the A, because multiplication is commutative, and that's how exponents work. And so this thing they've both calculated, this is the key. It is the common secret. So Alice and Bob now share the common secret K. In order to see why this is good, you have to think about what someone who's not Alice or Bob sees. Namely, again, Alice and Bob are communicating out in the open is how we're imagining this, because even if they're doing this by computer, their data is bouncing all over a bunch of computers who could presumably snoop on it or whatever. But what does everyone else see? Everyone else sees G to the A and G to the B. And because Alice and Bob had to agree on G and P, they also know G and P. But someone who knows only these four things cannot calculate g to the a to the b unless they figure out what a is or what b is. And here's the key. In order to figure out what a is, someone has to solve the discrete log problem on the number g to the a. In other words, they have to look at a number and answer the question, what power of g is this? And they could equally well look at g to the b and say, okay, what power of g is this? So, in fact, someone who's trying to solve this has a pick of two discrete log problems. Whichever of these two discrete log problems they want to solve, they can solve. And as soon as this person, who's not Alice and Bob, figures out A or figures out B, then they can calculate g to the a to the b, or g to the b to the a, and they'll also know the secret, and then everything falls apart. But seemingly the only way that they can do this is to solve a discrete log problem modulo a large prime. And remember, this discrete log problem should be difficult. It should not be possible for this third person to solve this discrete log problem if this prime is large enough. Now, last note. How do we know that someone has to calculate A or B in order to calculate g to the AB? In other words, how do we know there's not some other way? Like, for example, you might be thinking right now, g to the a times g to the b is g to the a times b, which is the thing that Alice and Bob both calculated. And I don't need to know a or b, I just need to multiply these things together, and I'll get that. And life will be good. However, the reason why that's bad is that that's not actually how you add, or that's not actually how you multiply things with exponents. This is actually a plus, so no good. But that's a really important point, actually, which is that if multiplying these two things together did give you g to the ab, then this whole system would break completely. So, why do we know that you can't actually find a way like this, but that actually works? Well, as so often is the case, we don't really know. We just hope so. All right, that's all for Chapter 3. To start next week, we're going to talk about RSA, which is the other big cryptosystem, the one based on factoring that we're going to talk about. And then we're going to talk about breaking these cryptosystems. That is, we're going to talk about some algorithms for solving discrete logs, which are hard, but obviously not impossible, because if you just guessed every power, you'd eventually figure this out. So we'll look at some better algorithms for calculating discrete logs, and we'll look at some better algorithms for factoring, and see how large the sort of inputs are where we can break these things, and see how safe we feel with the size of inputs that are actually used in modern cryptography. All right, I'll wrap up there for now, and I'll see you all next time.